And this is joint work with a bunch of different collaborators, both with expertise on the soil and plant science side, as well as computer scientists. And my co-lead on the project is Dr. Rich Wolski, and he's here today. And we are computer scientists, and our background, our expertise has been in cloud computing. And if you think about cloud computing, it has transformed our lives in terms of e-commerce. Every day we're using technologies that make our lives easy, and it helps us get instant access to information and connect with people all over the world. These are services that are available via our web browser that these companies are creating for us and giving away for free for us to use in order to make us better consumers. They're accessible to everyone, right? And you don't have to be a computer scientist to be able to use Google Maps or to use Amazon.com to buy your goods. And these companies are doing this seemingly for free, but not really. You're actually paying, but not in dollars, but in data. And these companies, as you use these services that are online for social networking or to buy things or to map out where you're going, are collecting lots and lots of information about you. Not just about the actual use of the software, but where you live, who you are, how many children you have, what kind of car you drive, who your friends are. All that they can infer and collect from these different services. The way these companies work is they take all this data, it's all data-driven, not modeled, just data-driven, put it together into these big, large computers, apply some really complex but well-understood math and statistics to this data, and then they're able to extract inferences and even better predictions of the future about things like what products you will buy, what products you will want, who you will vote for, even sometimes before we know it. So our research at UC Santa Barbara is to ask, well, this technology is amazing. It's turned us into very efficient consumers. It's not all negative. We buy things better. We find what we want faster. It has really improved our lives. Can we take the same type of transformation, cloud computing plus data analytics, and apply it to the hard problem of precision agriculture or agriculture decision making in order to meet some of the very important needs that are impending today? It's a prime area of opportunity because there's vast amounts of information surrounding the crop life cycle. And the analytics, this big data revolution hasn't made it to ag. There's a lot of amazing people in this room who are doing some things piecemeal, but you really need all the tools that Google and Amazon are bringing to bear. Those are available, they are accessible. We just need to be able to bring them to you in a way that you can consume them and use them for your science. If you think about it from a computer systems perspective, there's a lot of problems we have to solve in order to make this super simple and effective. We have the data acquisition problem. There's tons of different sensors. They come and go, they die, battery runs out. They have to be everywhere. As we've heard from our talks this morning, there's one takeaway, is that we need lots of sensors and they need to be on every single plant. Data fusion. If we have image data and sensor data, how do we combine that? Analytics, all the inferences and predictions that we want to make in lots of different ways. There are techniques being developed today that are presented at KDD that we'll want to use in the future. We have to be able to apply these new ideas as they emerge to the data. So we have to have some way to store that data and keep it and share it so that everybody has access. And that's got to be super, super easy to use. Non-computer scientists have to be able to take advantage of this so that we can advance science quickly. We don't have a lot of time. And one thing that hasn't been brought up yet, but I think is really important that we discover all the time in the ag space, is privacy. A lot of time, most of the time, technologies today, farmers give away their data. It turns out that the data is almost as valuable, if not more valuable, than the crops themselves. And we'll talk more about that. So we need some sort of mechanism of control for the farmer. The way it works today is you buy a piece of equipment like a tractor or a set of soil moisture sensors from a company. that those technologies then talk over the wireless, if you have it, if you're lucky. Otherwise, it goes over cellular, which is very expensive. Tons and tons of data is being transmitted to a remote cloud, a remote compute center that the company is in charge of. The company then applies this math and statistics, just like Amazon and Google does, to your data, and is able to extract insights from this data. Again, as the farmer releases his data by using this equipment, that data becomes under the ownership, in many, many, many cases, if not most, of the company. The company then, just like Amazon and Google, for advertising purposes, marketing purposes, can make lots and lots of money. In fact, most farmers have to then pay for a service to get their data back. And so it's not really working to the farmer's advantage right now. And so we want to design a new system and make it freely available, that instead of moving all that data to the code's tiny. Move the code to the data. You do it all the time. I'm sure most of you have a smartphone, and most of you have apps that you've downloaded on that smartphone. It's possible. We have the capability. So we want to take that math and statistics, put it in a box, put it on farm, make it super easy to use so that the farmer directly can extract those insights. In order to do this, we need in sort of ancient terms, it's a small supercomputer, but it's completely self-contained. It's called an edge system. An edge cloud is something that we're working on. This is a system that does all the acquisition and the fusion, but it also does the analytics. It gives by doing this, it gives the farmers full control over that data. And the systems challenge, again, is how do we make this completely fault tolerant, completely lights out management, because you don't want to be servicing a computer or employing an IT staff. This is really important. It's got to be like your refrigerator. You know, it opens up. You don't know why it's cold in there, but the light comes, and why the light comes on, but it does, and you're happy about that. But you don't need to know why. And when it doesn't happen like that, you know who to call. And that has to be our model. The other thing that we do that's different is that we work really hard at making this edge system look the same, behave the same as Amazon's cloud and Google's cloud. So any piece of software that executes out there, your MATLABs, your analysis in R, your C++ that we heard about this morning, any type of web service that you're writing, all of that, if it executes on Amazon, also executes on this box. And then when you need the code, when you say a scientist in this room comes up with a new application, you can put it on an app store. I, as a farmer, could easily download it to my system or get it in some other form and use it directly. That's our model. So a lot like Dr. Schnabel talked about this morning, we have a bunch of sensors and a bunch of very low power, very inexpensive computing devices that collect all of the information from the farm. There's they all talk via low power radio. There's a wireless that we set up just privately, just on farm, really inexpensive, really low power, that allows you to access that data. The farmer can access that data. And then we insert the edge cloud in there, on that wireless network to do the analytics, to do the hardcore analytics and some multi-analytics. You can do all kinds of different things in this one box, and it's survivable. It's a survivable system. If you are fortunate enough to have an internet connection, which most of our farmers are not, it's very high latency. It takes a long time to get an answer back because it's far away. With an edge cloud, it's on your property, instantaneous. So real-time decision-making, a lot like the watering system we heard about from Dr. Schnabel this morning, where we could look ahead just a few meters and understand how much water the plants need today, right now. We use Arduinos. This is the low-power technologies I was talking about, and Raspberry Pis as well. We leverage a lot of technology advances and protocols so that we can easily communicate data between these devices. And our edge clouds are these little bricks from Intel Next Units of Computation, called NUCs. And they're really hardened. They go up to 125 degrees, probably even more, Fahrenheit. and they're resistant to dust. They're really tough. It can run off of solar power. All this can run over solar power if you don't have electricity out there. So it's totally possible today, and it's very inexpensive. So that's why I think it's different today. That's why I think it's really important to pursue now. In terms of the analytics that we can perform, I want to just emphasize that we want to have these data sets that are shared and available, but that we can use in different ways. Because as we come up with new ways, we want to go back and apply them to the data we have. One example is that one that's in our paper that we have here in the top left is wine grapes. And one of the authors in the paper, our co-author, does precision farming. He does differential harvesting, use a really basic Kriging technique to do interpolation of a bunch of samples and distinguish wine grapes into red and yellow, which are high and low quality grapes. And then would run the differential harvester to actually do the splitting between high and low quality grapes. And he determined that for 99% accuracy, he was able to do that. We use that same data set, and this is Google Earth down below, to do something that was completely agriculture agnostic. It was a very simple technique based on point of origin analysis that said, if there were two groups that behave like this, what is the most likely point with 95%, I guess 99% confidence of where the origin point would be? And it's marked in that image. And what that shows you, if you look, little spots on the image, the one to the left is a tree and the one to the right is a watering hole, where the water comes out, the pump, there may be a water problem. It helps you focus in on where the problems may be. Again, this has to be collaborative research. One other thing I want to emphasize is we have to work together, not as just scientists across disciplines, but we got to get industry involved. There's lots and lots of great startups that we work with. It's amazing for students. My students all worked in cubicles, and they've rarely met any kind of animals, and they've had tremendous experiences out in the field to work with a lot of different students from other disciplines. And I think this is really the future. And just want to give a word of thanks for our supporters. NSF is the big one. Also the California Energy Commission. And if you have any questions, I'll take those now.